All right, so now we're going to talk a little bit about measurements again, and we're going to talk about these things called significant figures. So in science or in anything, we're going to use instruments to measure, to make measurements. And when we make a measurement, that measurement we have to recognize isn't a perfect measurement. It's not exact measurement. For example, if I have a nickel and I put it on a balance in my lab, I might get a mass of 5.002 grams. Okay? Nickels have masses that are about 5 grams. About. Some are a little bit less, some are a little bit more, whatever. The one I've got weighs 5.002 grams according to my balance. Okay? What we need to recognize is that that last number that balance gives us isn't perfect. There's some error in that last number because my balance can only read a three significant figure or three decimals. There's actually more. It could be 5.0022 or 5.0026 or 5.0019 and more, right? So the decimals are infinite, but the instruments we use to measure can only give us a certain amount of decimals before it starts giving complete error. Okay? So the balance I have in my lab can measure to 3 decimals. The 5, the 0, and the 0 are considered exact, meaning that if I was to make the measurement multiple times, I would get 500 something. Could be a 2, could be a 3, could be a 1, whatever. Okay? So what we're going to recognize is that when we make measurements, the last number that we have in our measurement is going to be where there's some error. Okay? So, when we deal with measurements, we need to recognize where that error occurs in our measurement. And that error should always occur in that last number. And any numbers after that shouldn't be there because they don't matter. Okay? These things are going to be called significant figures. The number of significant figures in a measurement, in the value of a measurement, is going to tell us the precision of the measurement. Okay, so now we need to back up a little bit further. We have 2 words that we use kind of interchangeably in the English language: accuracy and precision. But we need to recognize in science they are very different. Okay? Accuracy, when we take a measurement, the accuracy of the measurement tells us how close that measurement is to the actual value. Okay? The actual true value. The precision of a measurement, precision is how close measurements, repeated measurements, are to each other. Precision has nothing to do with how close the measurement is to the actual value. Okay? Precision is if I make multiple measurements, how close those measurements are to each other. Or if I make measurements with an instrument and you make measurements with an instrument, how close they are. All right? So we can see here, define precision. Precision is a measure of how close together repeated measurements are to each other. That means repeated measurements of the same thing. So if I took that nickel and I put it back on the balance, I might get 5.001 grams or 5.003 grams. Okay? That last number, that's where the error occurs. That's where the precision stops. All right? If I used a different balance, one that wasn't as good, I might get 5.00 grams, or 5.0 grams, or 4.9 grams, or 5.1 grams, okay? Depending on the quality and accuracy of the balance, I might not get as many decimals as I get with the one in my lab. So let's talk about this a little bit differently. Let's actually look at a measurement, okay? We're going to use 2 different rulers here to measure this nail. And maybe you do a measurement and I do a measurement. So, this first ruler has marks only at, we'll call this centimeters, even though it's not perfect, at the centimeters, like 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, and so on. And we can see there's quite a bit of space between each line. So theoretically, in my mind, I can separate that into 10 different little slots, right? So maybe the middle is like right here. So like 5.5 might be about right there, might be a little bit to the right. So I might read this as 5.3 centimeters, using only one decimal. Okay, let me write that again because my centimeter didn't come out very well. Centimeter. Okay, if you read that, you might read that as 5.4 or 5.2. Okay, so that's where that precision comes in, that error comes in. If I read it, I might even do this the next day and read it as 5.2. Right? So it's that last digit there that might change a little bit when we make a measurement. Now, if we use a little bit better ruler with more demarcations, where now I've got millimeter marks, I might be able to read this a little bit better, right? Maybe it's somewhere in here. So I might be able to read it as 5.35 centimeters now. And you might read it as 5.30 centimeters. Okay? But now, because I've got a little bit better instrument to make the measurement, the error occurs in another decimal. Okay? That's what precision is. Where that error first occurs. And it depends on the instrument we use. You can see two rulers here. One's going to give me a little bit more precise measurement than the other because it's got more marks on it. All right, so let's take my number 5.002 grams. That was the mass of the nickel. Okay, so I want to determine the number of significant figures in this value. And there are 4 rules, and they're pretty easy to follow. Okay, any non-zero number in a value is significant. So in my value 5.002, the 5 and the 2 are considered significant because they're not zeros. They mean something. Okay? Any zero between non-zero numbers is significant. So we can see we have a 5 and a 2 and there's zeros between them. Those zeros that are between the 5 and the 2 are also significant, meaning that they are part of the precision of the number. Okay? 2 other rules. We really only cared about zeros, because zeros are the things we have to determine if they're precise or not. Zeros at the beginning of a value, those are called leading zeros. I'll write that down here. Leading zeros. Are not significant. They're only there to show us how small the number is. Okay? So zeros at the beginning of the number aren't significant. Zeros at the end of a value, these are called trailing zeros. Oof, my pen's not happy today. Trailing zeros. Are significant if there's a decimal in the value. Okay, so if there's a decimal anywhere in the number, the trailing zeros are significant. So 5.002, the 5 and the 2 are significant because of our first rule, and the 2 zeros are significant because of our second rule. So 5.002 would have 4 significant figures. I'm going to write that as SF, significant figures. Okay, so let me give you another number. 0.05002. So now the 5 and the 2 are significant, and the zeros between the 5 and the 2 are significant. But we have a 0.0. Those are leading zeros. Zeros at the beginning of a number. I apparently spelled 0 wrong, so 0 is wrong. Should be an E in there. But those zeros at the beginning of the number are leading zeros, and they are not significant. So 0.05002 also has 4 significant figures. What if we do 5.00200? 5.00200. So the 5 and the 2 are significant from rule number 1. The zeros are significant between the 5 and the 2 because of rule number 2. There are no leading zeros here. We have 2 trailing zeros, but there's a decimal. So those 2 trailing zeros are significant. So 5.00200 has 6 significant figures. 1, 2, 3, 4, 5, 6. Okay? So we're going to follow those 4 rules to determine the number of significant figures in a value. Non-zero numbers are significant. Zeros between non-zero numbers are significant. Leading zeros are never significant. Trailing zeros are significant if there's a decimal. That's it. 4 rules. Okay. One other thing I want to note here is that you should make it a practice is that if you have a decimal and there's no number in front of the decimal, put a 0 there. So for example, we should write 0.74 instead of 0.74. And the reason for this is that decimal sometimes can get pretty small. Or if you're writing on if you've erased a couple times or written on a piece of paper or whatever, that decimal might get missed. And in medicine, if you miss that decimal and you read that as 74 instead of 0.74 and you're delivering medicine, you might kill somebody. Let's not kill people. Okay? So, if you put that 0 in front and somebody sees it like this and misses the decimal, they're like, well, why the hell did they write a 0? It's because there should be a decimal there. Okay? You don't write a 0 in front just for the hell of it. So make it a practice. If you've got a decimal and then your number, put a 0 in front of your decimal. Right? If we're dealing with numbers in scientific notation, they're really easy. If we look at that decimal piece, that number up here, 2.060, if we have it in correct scientific notation, how many ever numbers we have here is how many significant figures we have. We don't ever worry about the times 10 to the 5. Okay? That decimal piece is where we get our significant figures from. In this case, 4 significant figures. This has 3 numbers here, so this has 3 significant figures. Okay? So scientific notation is really easy to tell how many significant figures you have. So here's a bunch of examples. Okay? All non-zero, right? Anything non-zero is significant, so this would have 1, 2, 3, 4, 4 significant figures. Zeros between non-zero digits, like 3.05 or 2.006, those zeros count. So this would have 3, and this one would have 4. Remember, that last number, that last significant figure, that's the one that can change if we repeat the measurements. All right? Zeros to the right of a non-zero digit, I call those trailing zeros, or at the end of the number. So those, remember the 4 counts? The ones in front, those are leading zeros, they don't count. But if there's a decimal, the trailing zeros count. So those 2 at the end count because there's a decimal. Okay? There's a 2 here, and then there's 3 trailing zeros, 3 zeros at the end, but they're all significant because there's a decimal. It doesn't matter where the decimal is in the value, but if there's a decimal, any trailing zeros count. So 11,000 decimal. That decimal there makes those significant, those trailing zeros, those 3 zeros at the end, significant. If there's no decimal at the end, they're not significant. So this would have 5, this one would have 5, and this one would only have 2 because there's no decimal making those trailing zeros significant. So that means in this number, that first one, 11,000, 11,000, any error, any change in the number would occur in that last 0. In this second one, 11,000 without a decimal, my error would occur in that thousandths place. Okay. Scientific notation, we said that all the numbers in that decimal piece in the front there are significant all the time. So in this case, there's 3 there, so it's 3. Leading zeros here, not significant. Doesn't matter if there's a decimal or not. Leading zeros are never significant. So the only 2 significant figures are the 2 and the 5. And here, 0 in the front, that's not significant because leading zeros are never significant. For 0, there's a decimal, so that trailing 0 does count. 6,000, trailing zeros, no decimal, those don't count, so only the 6 is significant. And 340, the 3 and the 4 is significant, there's no decimal, so that trailing 0 is not significant, so there's 2. The number is still 340, but if I was to repeat the measurement, I might get 330 or 350. Okay, that last significant figure is where the error occurs. Exact values. There are times when we have an exact value, and an exact value has an infinite number of significant figures. Okay, usually a lot of zeros at the end. An exact value might be like multiplied by 2. So if I need to double a value, I'm multiplying by 2. That 2 is considered exact. Okay? Or if I have, let's say I measured the radius of something. Remember, you have a circle, the radius goes from the middle to the outside, and the diameter goes from one side to the other through the middle. So the diameter is always 2 times the radius. So if I measure the radius and multiply by 2, I get the diameter. That 2 there is exact. You're exactly doubling whatever you've got. Okay? But you can also get exact numbers in measurements. If you're counting a small number of things, or they don't move around and you can control them, you can get exact measurements. For example, a deck of playing cards, excluding like jokers, just playing cards, there's 52 cards. There's 4 of every one. There's 4 aces, 4 twos, 4 threes, 4 fours, all the way up to kings. That's 52. So if you have a deck of cards, you can count how many cards there are exactly. Or if you're in a classroom and there's a small number of students, let's say 10 or 11, and you tell them to sit in place, nobody can go in or out or move, I can measure those students, how many there are, simply by counting. Okay? But if I've got a room of 100 students and they're allowed to move around, then me counting them correctly is going to be really hard. Or if people are allowed to come in and out, I'm not going to get an accurate measurement. Okay? So there are definitely times when you can have exact measurements, especially in counting things. Also understand that metric conversions are exact. So 1 kilometer is exactly 1,000 meters. Okay? And some conversions in the English system are pretty much exact. 1 foot is equal to 12 inches exactly. Okay? It's when we go from one system to the other, metric to English or English to metric, that those conversions might not be exact. Okay, here's practice. Again, pause the video for a little bit and go through and see if you can get the correct number of significant figures. Okay, and then start the video again, and I'm going to go through them. All right, so pause it now, try it, see what you get, and then start again. Okay, so hopefully you paused it now, and I'm going to show you what the significant figures in each of these values is. Okay, 4 rules, right? Non-zero numbers are significant. The 4 and the 5 are significant. Zeros between non-zero numbers are significant, so that 0 is significant. Leading zeros are never significant. And trailing zeros, this 0, is significant if there's a decimal in the number. And there is a decimal here, so that one's significant. So this one has 4 significant figures. 14,000. The 1 and the 4 are significant. We have trailing zeros here, but there is no decimal. So those zeros are not significant. So this would have 2 significant figures. It means that if I make another measurement, I might get 15,000. The error's in that thousandths position. Okay? 0.00023. The 2 and 3 are significant. Those are leading zeros. They are never significant, so that has 2. 2030, 2030. The 2 and the 3 are significant. The 0 between the 2 and the 3 are significant. That trailing 0 is not significant because there's no decimal. 3. 20.0010. The 2 and the 1 are significant. The 3 zeros between the 2 and the 1 are significant. Is that 0 at the end significant? It's a trailing 0. It's significant if there's a decimal, and there is. So that's significant. So this has 1, 2, 3, 4, 5, 6. 6 significant figures. That means if I make a measurement, it's that 0 at the end that might change a little bit. Okay. Scientific notation. We said that scientific notation, all the numbers in the front there, all the decimal piece are significant. So this is going to be 3. 0.0004. The 4 is significant. What about those? Those are leading zeros. They are never significant. That has 1. 91.0. What do you think? I think 3. The trailing 0 is significant because there's a decimal. And 7.2 times 10 to the negative 5. It's scientific notation. So I have 2. Hopefully you're good with that. If you're not, please come to office hours.